Well, hello everybody, and welcome to another edition of AP Chemistry Fun. And today we want to talk about this idea of Coulombic attractions and where are you going to find it. Now, Coulombic attractions are very important because they show up everywhere in the AP exam. My guess is you're going to see 6, 7, maybe even 8 questions related in some way to Coulombic attractions. So let's get into that. Consider the data in the table below. Explain in terms of Coulombic attractions. Here we go, Coulombic attractions. Why first ionization energy of sodium is greater than that of potassium. Good. So first, I think we need to get some notes regarding Coulombic attraction. So I love to make concept maps. So let's make a beautiful concept map. And let's start up here with Coulombic attractions. So Coulombic attractions. Great. And where I always like to start is, let's get a definition. What are my Coulombic attractions, right? Well, Coulombic attractions are what? It is a force of attraction between a positive and a negative body, between positive and negative bodies. Good. So that could be between what? A nucleus and an electron. It could be between a cation and an anion, right? It could be between the positive pole on one polar molecule and the negative pole on another polar molecule. All of those are Coulombic attractions. Now, we could have a positive and positive. In that case, it wouldn't be a force of attraction. It would be a force of repulsion. Or I could have a negative and a negative between two electrons, and that's still a Coulombic force, but it's a force of repulsion. In this case, we want to focus just on the attractions, so we're going to focus on the attraction between a positive and a negative body. Great. Now, we can explain a lot of these forces based on something called Coulomb's law. Coulomb's law, right? There we go. I don't know who Coulomb is, nor do I really care, but he has a pretty, or she has a pretty good equation. It says that the force of attraction between a positive and a negative is equal to K, Q1, Q2 over R squared. Now, K is a constant. I don't know what the constant is, but it's a constant, so I don't care about it. Q1, I like to think of as my charge of the positive body, whatever that positive body is. Is it the cation? Is it the nucleus? But it's the positive particle. Q2 I look as the charge on your negative body or the negative particle, and R is simply the distance between your bodies. Good. So that's what Coulomb's law is all about. And just real quickly, we can do some basic math, right? And just think of relationships. As my Q1 increases, what's going to happen to my force of attraction? Well, my Q1 goes up, so that means my Coulombic force of attraction goes up. As my Q2 goes up, what happens? Once again, it's in the numerator, so my force of attraction goes up. And as my R, as my distance between my particles goes up, my force of attraction goes down. It's an inverse square relationship. Good. Perfect. So that's a little background on Coulomb's law. Now, where do I see it showing up in the AP curriculum? And I think of it, I think it shows up in two places, really. Well, two broad places. So we're going to, really, there are two types of Coulombic attractions that I experience in chemistry. And you can break this down another way if you wish, but I kind of like it this way. And I'm going to call them weak Coulombic attractions and strong Coulombic attractions. And this works out real neat for me. And you might like it as well. So here, let's take a look first of my weak Coulombic attractions. These are really my IM forces. My weak are my IM forces. So things like my London dispersion forces, which we have to now say are what? On the AP test, remember, they may not give you credit for London. You may have to use the words induced dipole. I use both. I'll say London, and then in parentheses, I'll say induced dipole. So my London forces are weak Coulombic attractions, and my dipole-dipole interactions are weak Coulombic attractions. And then off of that, I consider my hydrogen bonding a subset of my dipole-dipole, right? It's a special case of dipole-dipole. But all of those are weak Coulombic attractions. And let's take a look, just as an example, let's consider our hydrogen bonding in water, right? So if we have water here, remember water looks something like this, right? It has an unshared pair, two unshared pairs, and some hydrogens bonded to it, right? And I have another water, and it would maybe line up like this. And here are my hydrogens, and there's my oxygen. And remember that this side of my water, because of the electronegativity of oxygen pulling these electrons into the bonds with hydrogen closer to it, this side of my water is a partially negative, and this side is a partial positive. And this side is a partial negative, and this side is a partial positive. Now, what do I have? I have an attraction between, positive, yoink. I have an attraction between this partial positive side of this molecule and the partial negative of this. And here's my attraction right here, right? Right there's my attraction. That is a weak Coulombic attraction. It is between the partial positive on one water molecule and the partial negative on the other. And its strength is going to be driven by Q1, how strong this partial positive is, Q2, how strong this partial negative is, and R, how close those molecules get together. And so that explains the strength of my hydrogen bonding in terms of Coulombic forces. We'll get into this in more detail as we look at some of the questions. All right? But let's go up here to the other type. We have strong types of Coulombic attractions, and these are my, what I consider mainly my bonds, right? My strong are my bonds, my bonding, what we consider real bonding, right? So my ionic bond, right? This is a strong Coulombic attraction between cations and anions. And then I have my covalent network, or my covalent bond, right, which is a strong attraction, Coulombic attraction between the nucleus of one atom and the valence electrons of another atom. Or we can have a covalent network, which is a bunch of atoms bonded to each other in a covalent way. And then we could have metallic bonding, which is my sea of valence electrons surrounding my metal cations. These are all examples of strong Coulombic attractions. You know, think back here. Let's go back to my ionic bond, because that's the easiest one for us to see. In my ionic bond, what do I have? I have a cation, so something like a sodium cation, and it is attracted to a negative anion, right? So here's my Q1, here's my Q2, and how close these can get is going to be my R. And so in all of these cases, we can explain certain aspects of the relationship using our Coulombic attraction. Now, we'll get into this in a little detail, but first, let's go back to our question and let our questions drive this. All right, here we go. So we want to explain in terms of Coulombic attractions why the first ionization energy of sodium is greater than that of potassium. So we want to look at my potassium and my sodium and here are my ionization energies, and they said, why is this sodium ionization energy greater than my ionization energy for potassium? Well, here we go. What is ionization energy? Ionization energy is the energy required to remove an electron from an element in its gaseous state. So what we have to do is we have to remove an electron. Well, the question is, why isn't the electron there in the first place? And the answer is it's held there by a Coulombic attraction between the nucleus and the electron, right? Good. So really, my ionization energy is going to be a function of, so it is a function of my Coulombic force, we'll call it Coulombic force, of attraction between the electron and the nucleus. Okay, great. Good. Do we have something over here to help us? I don't know. Let's go back. Did we see anything specifically in our notes about this over here in my types? Okay, we need to look at my types. And what do I see? I've got weak, and I've got strong, and I have bonding. But where's my relationship between an electron and a nucleus? Well, we need to put it in here. It is what I would call, and I'm going to need more space. We need to go, it's so strong attraction. And we're going to extend the page. Good. And we're going to call this my intra-atomic attractions. Okay, so intra-atomic, intra means what? Within, atomic, the atom. So we're talking about things within the atom. So what we're talking about here is the attraction between the nucleus and an electron. In case of ionization, we're usually talking about the nucleus and the valence electrons. So then, how does Coulomb's law manifest itself here? Well, my Q1 is going to be my Z effective, my effective nuclear charge. My Q2 is going to be the charge on my electron. And then my R is going to be the distance from the nucleus to the electron, right? And if we're talking about my valence electron, what is that? The distance from the nucleus to the valence electron is what? My atomic radius. Good. So those are the key ideas. Q1 is my Z effective. R is my atomic radius. Okay, so now let's go back to the question. Maybe we have enough information now to answer that. Good. Zoink. There we go. Woo. So ionization energy is a function of Coulombic forces between my electron and my nucleus. My Z effective can be considered my Q1. My atomic radius is equal to my R. So as my Z effective increases, my force of attraction increases, and then my ionization energy increases, right? And as my R increases, now R, where is it? Remember, K, Q1, Q2 over R squared. So R is in the denominator. So as my R increases, my Coulombic force of attraction decreases, and so my ionization energy would decrease. All right, so I think we can now do battle. Let's take a look at Z effective. My Z effective, and I'm defining it as Z minus core electrons, is 1 for potassium and 1 for sodium. So it has no impact. So we're going to focus on what? Atomic radius. Good. My atomic radius in potassium is 1.9. Let's go back to our question. Why is sodium greater? Great. And here's my sodium, 1.5. So here's what I'd answer. So my ionization is a function of Coulombic attractions. The atomic radius in sodium is smaller than that in potassium. So the Coulombic forces are greater in sodium. Thus, sodium has a higher ionization energy. Great. Now, at some point, you may want to, for the AP reader, explain your Coulombic attractions that they, as we did here. Make sure you clarify to the reader that you know what you're talking about with these Coulombic attractions. All right? So good. I think we've clarified it, right? Sodium, the atomic radius of sodium is smaller than that in potassium, so the Coulombic forces are greater in sodium. Thus, sodium has a higher ionization energy. Good. Let's see if we can do the next one. Is the ionization energy, is the ionization energy of lithium greater than, less than, or equal to that of sodium? Okay, so let me get rid of some of these lines. I'm getting confused, and that's easily done with me, as you all well know. Good. Oh, good. Woo, yay, it's all gone. I love that magic. Watch this quarter in my hand, and it's disappeared. Great. Now, I want to figure out right here. Lithium, is it greater than, less than, or equal to that of sodium? All right, great. So what am I going to do? I am going to, once again, what I'm going to look for my Z effective, and I'm going to look for atomic radius, because this is an intra-atomic question, right? My Z effectives are the same, so my only thing to work with are my atomic radii. Good. So here we go. Let's write the answer. I need more space. Here we go. All right. So since both have same Z effective, the atomic radius is determinant. It's going to cause the change, right? As atomic radius decreases, Coulombic attraction does what? Okay, right? R is in my denominator, so as my radius gets smaller, my Coulombic attraction increases, and then the energy required to remove that or to overcome that Coulombic attraction, ionization energy, increases. Great. So now, since lithium has an atomic radius of, what was lithium's atomic radius? Yoink, 1.34. 1.34, and sodium has an atomic radius of 1.54. Lithium has stronger Coulombic attractions between nuke and electron, so it will have a higher ionization energy. Great. Do you trust me? Do you believe me? Well, let's take a look at data. The ionization energy of lithium, according to Brown and LeMay, is 520 kilojoules per mole. And that indeed is greater than sodium. Perfect. All right, so let's see if you can do this on your own. Let's go to the next question. There it is. You guys read this. You bring me back when you're ready. You read it and do it and bring me back when you're ready. All right, here we go. Here's how I would answer this question. So I look at this, and once again, this is my interatomic. When I'm dealing with ionization energies, I'm dealing with an intraatomic relationship. That means my Q1 is going to be Z effective. My R is going to be my atomic radius. Now, Q2, do I care about it? No, because the electron charge is always staying the same. We're not varying the electron charge. We are only varying Z effective and your atomic radius. So those are the two things we have to look at. All right. So now, what was the proposal here? Why is sodium greater than, okay, so here's sodium. Why is it greater than aluminum? Why is sodium greater than aluminum? It's not greater than aluminum. Look at that. It's less than aluminum. So let's go back and change this. It is not greater. It is less than aluminum. It can't be greater. We have the proof right there. So let's explain why aluminum is greater than sodium. All right, what are we going to state? Ionization energy is a function of the Coulombic attractions between nuke and valence electron, right? As my Coulombic force increases, my ionization energy increases. Okay, good. We got that set. Now, we want to explain this. Aluminum has what? Oh, let's not go there yet. Let's talk about my Z effective. Let's talk about my Coulombic attractions. My Coulombic attractions depend on Z effective and what? Atomic radius. Bam. As Z effective increases, my Coulombic force increases, and as my atomic radius increases, my Coulombic force decreases. Good. There we go. So now maybe we can start making our case. So let's take a look. Aluminum has a greater Z effective, right? Z effective is 3 versus 1. Greater Z effective, 3 versus 1. And a what? Well, here's my aluminum. And it has a smaller atomic radius, 1.18 versus 1.54. 1.54. Both increase the Coulombic force and thus increase the ionization energy. There you go. I would say that is a reasonable answer to the question. Good. Is the first ionization energy of silicon greater than, less than, or equal to that of aluminum? So we're going to look at silicon versus aluminum. So I'm going to look at aluminum versus silicon. Great. Here we go. All right. I'm going to go ahead and start getting rid of some of this. Some of it I can use again, can't I? That's the magic of the board. I'm going to get rid of this down here. No. Good. Yoink. And for all you type A, we better get rid of that as well as this because you guys may not like that. Okay, so I can run with this other stuff. Ionization energy is a function of the Coulombic attractions between the nucleus and the electron, yes. As my Coulombic force increases, my ionization energy increases, yes. The Coulombic attractions depend on Z effective and atomic radius, yes. As my Z effective increases, Coulombic force increases, and as my atomic radius increases, my Coulombic force decreases. All right, so now we want to look at these, we're going to compare these two and these two. First of all, the Z effective of silicon is greater than that of aluminum, right? We're looking at 4 versus 3 for my Z effective. In addition, my atomic radius of silicon is smaller than that of aluminum, right? We're looking at 1.11 versus 1.18, right? Good. Both of those have the same impact, right? Both increase the Coulombic attractions in silicon. So silicon should have a greater ionization energy than aluminum. Cool. Now, indeed, let's check it out. The real answer is that silicon has a 786 kilojoules per mole ionization energy, which is indeed greater than that of aluminum. All right, let's call it quits right here. We'll go through, I have a couple other questions that we can answer next time. All right, see you then. Bye-bye.